is the best explanation. Yeah, cosmological constant is the best explanation, is the simplest one. But then, cosmological constant is also associated with a vacuum field, with a quantum vacuum field, which satisfies an equation, the expected values of quantum vacuum satisfy an equation of state of the form P equals minus density, right? But the value of the cosmological constant is like 120 orders of magnitude smaller than the quantum vacuum expected in. So that's also, the explanation theoretically looks well, but in practice it's one of the worst predictions ever because it's 120 orders of magnitude
cosmological constant
error, right? So quantum vacuum is not a good explanation for cosmological constant. So some people say, well, the cosmological constant is just a fundamental constant. Why it has this value? Because it has this value. So they say, why G, the gravitational constant G, has this value and not other value? But that's also not very easy because, see, it's still an issue because cosmological, the gravitational constant has a value, but this value is measured by specific experiments, torsions, the von Erdfusch, etc. It's measured. Any other constant, fine structure, Planck constant, all these constants are measured by experiments. And then they say, yeah, but the experiments to measure the cosmological constant is not possible because you cannot experiment with the universe. It's this observation. Anyway, there's an ongoing debate. Now, one possible way out of this debate is to say cosmological constant, 0. 0, 0, doesn't exist. The dark energy, all these things, 0, doesn't exist. So what would be the explanation? Change the geometry. We are not in an FLRW. This idea that we live in an FLRW geometry modified times small perturbations is wrong.
Left-hand side of ancient field equation.
Sorry?
Left-hand side of ancient field equation is the left-hand side of the...
Yeah, the left-hand side, exactly, exactly. We modify the geometry, the G, the Einstein tensor. So, one of the assumptions, what would be the effect is that we say no Friedmann-Robertson-Walker, instead LTV geometry.
Inhomogeneous.
Right, and then our null geodesic is going to be completely different. And therefore, we, in this respect, we take the data. Which are the data? The data are redshift, observed, luminosity distance, observed, and we have to check the consistency between them by seeing if the redshift if the distance that is given by the redshift agrees with the luminosity distance.
Excuse me, sir.
Yeah.
Is not luminosity distance dependent on the model itself? I mean, luminosity distance depend on the rate of
that's
the expansion thing.
Yeah, but luminosity distance is also depends on the absolute magnitude. It's a modulus that depends on the absolute magnitude. So it is much weaker dependence, and there is a distance that the luminosity distance has to agree with the redshift, right? It's the luminosity. The null geodesic will tell you a prediction on the luminosity distance, but that luminosity distance has to agree with the absolute magnitude estimation. Yeah. The point is, perhaps it's good to clarify. It's not that there are two distances involved. It's only one. It's a luminosity distance, but there is a luminosity distance that is predicted by the model, and there is a luminosity distance that is estimated by observations. We'll see that in a diagram. No, they're very, very... I'm confused because when I say something, people say... in Mexico, if you say For example, you ask me, is your shirt white? But if you ask me, is your shirt black? I'll say, but here I say something like, for example, I say something, you say, no. You say something, you say, no.
That means that we agree very much.
Yes, when you say like this, confusing, very confusing.
Sir, if you are going to make this very slow, it means also yes.
Yeah.
What?
Slowly means yes.
Slowly means
No, but
yes.
I don't know. We have the same thing what you are describing just now in whether we also say yes like this and no like
Indians
this.
are
Sometimes it
not
happens, I
different.
don't know.
That's not a
Indians are
concept.
sir, supernovas with a very far distance.
Sorry?
Indian people are supernova very far distance.
You're not
They
good
can't
standard
predict
countries. Now, going back to this, you have a distance, a luminosity distance that is observed, right? It's observed, so it's a fact. That has to be as far as that. And then that has to be fit by the luminosity distance that comes from the non-geodesics. That's why you see dots and curves. The curve, the geodesic, the luminosity distance is predicted by the model, but it has to satisfy the dots. Yeah, the observational dots. Okay, so if we change the geometry, then we might have luminosity distance that fit the supernova very well for a given redshift. So this is what happens. This is a big difference. This is another approach. Yeah, we don't deny the data, because I can say the universe is a black spider, or a red scorpion, or a blue tiger, but I can say anything. But here it's irrelevant what we say. We have to show that the theories fit the data. See, you always should, in science, there is data, and you construct theories that will fit the data. Never the opposite. You have a theory, you like it so much, and you try your data to fit your theory. That's wrong. Very human to do this, but that's wrong. That's not good science. That's junk science. So here is the opposite. We have data, and we construct theories that will fit this data. So here, LTB geometry, and why LTB? LTB is a very poor representation of inhomogeneity, because it's spherical inhomogeneity. It's very simple inhomogeneity. So why LTB? Well, because this is the simplest type of inhomogeneity. Because people, why not Kantowski-Sachs? Well, Kantowski-Sachs are not good because they are not inhomogeneous. They are anisotropic, but they are not inhomogeneous, right? Bianchi, the same thing. Now, LTV are good because they are inhomogeneous, but they are the simplest one. And also because once we started making measurements, and I am not an observational person. I mean, we as a community, scientific community, started making observations and relying on them, and more precise observations and so on. The field, which is cosmology, became flooded by astrophysicists. See, flooded. It's like, imagine that you are a particle physicist, and suddenly you are 30, 40, and suddenly 200, 300, 1,000 engineers come. Now, the engineers have a different mentality. Astrophysicists have a very different mentality from the former cosmologists, were more theoretical and so on. Astrophysicists came, say, give me your very simple, come on, inhomogeneity. What's the simplest model? And then you say, well, LTB, but it's very, I don't care, model. And then all of them, compute. plot, fit. Tell them, yeah, but look, these are models that are very simple. That don't care papers, research grants, the prizes, conferences. They're happy about that. Compute. Those little ants or like that all the way. Compute. Okay? So that's the cosmology we have now. Cosmology
Because
has
we are
become
getting lots of data.
lots of data.
From all these
Exactly.
telescopes.
So you say, well, but what is dark energy? Compute. They are very reluctant to look at theoretical issues. They're always compute. But okay, but there's a limit to this. Comes a point when it's like you are having food, and they give you some very tasty food. So you eat, and you're very happy eating. People tell you, hey, wait. There comes a point you have indigestion. So we're now having indigestion of compute. There is now a need to look for theoretical explanations, right? Now there are some people, again, never for a minute think that the scientists are holy souls looking for the truth, completely objective. Total, absolute lie. Scientists, yeah.
If somebody discovers the nature of dark energy, then he will get Nobel Prize.
Yes, that's true. No, that will end the debate. Absolutely agree. Like compute. But then dark energy particle appears, dark matter particle appears, experiments, then Nobel Prizes, everybody's happy and so on. Yeah, agree. That would be the goal. Because then again, I'm talking about astrophysicists. Astrophysicists are not the ones who are going to do that. This would be done by particle physics people, right? So astrophysicists, they compute, fit statistics and so on. But there are particles, and like you can make predictions saying, well, everything is fine as long as I have a particle of this cross section or whatever. But these particles have to be found by particle physics, and that's another area. See, these people, particle physics people, have also gone into cosmology, but not into late time cosmology, but rather early universe cosmology. But this is different because early universe is a laboratory for elementary particles, right? So it's natural, but particle physicists have not discovered, there is no observation. Now, why is it so difficult to detect a dark matter and a dark energy particle? Because these particles, if they exist, should have formed and decoupled. Let's say the universe at the beginning, everything was in equilibrium. But then components begin decoupling, right? And decoupling from the early cosmic mixture, the early cosmic plasma. The only remnant of the early cosmic plasma now is the CMB, the photons. But before, it was like we all go in a family. We go to a picnic, right? I'm the photon, the neutrino, dark matter, baryons, etc. We are all together, a big family. We go for a picnic. Very soon, dark matter and dark energy, they say goodbye, picnic, take my own way, right? They decouple. Bad guys. They went away. But we're still baryons and photons and neutrinos. Then neutrinos say bye-bye. They go. Then we're photons, baryons, and electrons, right? Okay. Suddenly, the photons and the baryons, but suddenly the baryons and the electrons all say goodbye, and they free stream. So who's left? The poor photons alone. They go to the picnic alone, and then they are the CMB, right? So who decoupled first? The dark matter, and if there is dark matter particle, and And if there was dark energy particle, they should have decoupled very early. Why they should have decoupled? Because they are dark. Because they don't interact, right? That's why the coupling is no interaction, right? So they should have decoupled very early. That means that if we want to find them through an accelerator, we need fantastic energies, because they should have decoupled when the universe was extremely, extremely hot, extremely energetic. So if we want to reproduce these conditions, we need huge accelerations. Like, for example, the LHC, the LHC is a circle of 30 kilometers diameter, right? So that's very big. And look, we're already finding interesting results, but not yet the dark matter particle. The Higgs, yes, important, but not the dark matter particle. In fact, what the accelerator has been useful is to discriminate among different candidates of dark matter particles, but not found one, right? So it's very difficult to find them, right? So while we don't find them, then while we don't find these particles, and it's very difficult, it is very legitimate to ask the question whether it is possible to fit observational data without assuming the existence of dark energy. And some people go even further, saying perhaps also no dark matter. Now, doing away with dark energy and cosmological constant is possible with inhomogeneity. LTV models have failed because they are too simple, but it is not ruled out that a more complicated inhomogeneity could explain observations, except that it becomes too difficult. Okay? Now,
So
dark matter, let me just finish. This is to get rid of dark energy, right? And to get rid of cosmological constant. Because this is observations at a very large scale. But dark matter is more difficult to get rid of, because the dark matter is supposed to be concentrated around the galaxy. So it's much closer, right? And if we assume there is no dark matter, we find it very difficult to explain structure formation. That means if there is no dark matter, the map of distribution of galactic clusters that we observe would be very different. The so-called power spectrum, it would be very different. So it is very difficult to get rid of dark matter unless we assume that general relativity is not the gravity theory. And this has given rise to modified gravity theories. Modified gravity theories means either some generalization of general relativity or some other theory. There are several candidates. And also these candidates could explain the so-called acceleration of the universe. The fact that we need a cosmological constant implied an accelerated expansion. Yeah. Now, perhaps this is in general relativity theory with FLRW geometry, but modified gravity theories have shown that you can also obtain an accelerated expansion without cosmological constant with an FLRW geometry, as long as you modify the gravity theory, right? Okay, so yeah.
That LTP model we are considering inhomogeneous fluid and all.
Yeah, sure.
Yeah. So, but what about and it is spherically symmetric?
It's spherically symmetric.
So what about it's also, we can say it's anisotropic, or?
It is anisotropic, but the idea, that's a good question. LTV model, what type of LTV model?
Yeah.
It's an LTV model with negative special curvature, because negative special curvature is also a fast expansion. But it's not as fast as cosmological constant, but quite fast. And it's also the idea that the universe where we live, the observable universe, is not homogeneous, but it's a sort of underdense region. That we live in the middle of a huge underdense region. So it's a density void. Now, this is an assumption that has to be tested independently, whether we live in a low density region. we know that there are low density regions, but they are not as big as the observable universe. So again, first we say, let's test an LTV model to see how it works. And then there come other questions. See, it's like the idea, first I make you an offer. You want to buy this chalk for 1,000 rupee? No. But 100 rupee? Okay. And then you are, okay, that's first stage. He said yes. Now, second stage is he's going to say, well, but what is this made of? Then there is a second stage. So first you propose a model and test it. And then passes the first test. And then comes other tests like this. See?
So now, but what we can say about anisotropy?
No, we can say that if we are near the center of this large density, under density, then everything is isotropic. Because remember that the observer, if you're in the center of an explosion, then the world is isotropic. The spherical symmetry admits an observer that is completely isotropic, the one at the center.
One at the center,
Yeah.
yeah.
The other observers detect anisotropy. Now, if you are far away from the center, again, the example of the explosion. If you stand at the center of a spherical explosion, you see all things coming out isotropically. If you are in the center.
If you are in the center.
But if you are riding in one of these, if you are riding in an expanding object that is near the center, then you see anisotropy, but not much. Now, if you are further away, it is extremely anisotropic.
So it depends on the value of a small r.
You have to be for an observer, and this is an important question because people say, well, how do you make an LTV model compatible with the CMB?
Yeah.
Well, how? To put the observer very near the center. You put the observer very near the center, then CMB is isotropic.
Then it will be a special case, no?
It's not nice because it means that you have a region where that is favored. You have a certain region of the universe where people see things very nicely, and then the rest where people see observers there is something that is untestable, right? Because we cannot go take a spaceship and in 500 million years to go somewhere and then come back and report. It's untestable. But philosophical is not satisfying because it would mean that we as an observers would be living in a very special region of the universe. See? That's a bad thing about LTV models. But this is only because the inhomogeneity described by LTV models is extremely crude and simple, right? But more different forms of inhomogeneity would remove that. And also, okay, let me just show you what I've been talking about here with more detail, okay? So, light cone structure in an LTV model is much more complicated than FLRW. So we're assuming, let's suppose we are in the middle of a very large density void. So the assumption is as follows. Say this is, what we're assuming is that there is a very large overdensity. We are located here, right? And this is the observable universe. This is the observable universe, and we are here, right? Okay. Now, if we are here near the center, right? This you rotate, right? You rotate to get the picture. Is that understood? Yeah. Okay. So, if you are here, then your observations reflect isotropy. Everything will be isotropic if you are here. If you are near here, then observations are almost isotropic, not very different, right? But if you are here, then your observations will be extremely anisotropic, right? Okay? So you might explain, if we're here and a supernova is here, we might explain the correct distance redshift relationship for supernova if we are here. But then CMB is problematic. So the question is, how further away can we be from the center to comply with CMB? And we have to be like 10% of this distance. If we are within 10% of the Hubble distance, near around the center, that's we're close to the center, then we can, remember the CMB is not perfectly isotropic, it has anisotropies, right? Okay, so we have to be like 10% of the center of the distance of the observable universe. Right, so we would have to be like 100, 200, like 300 megaparsecs away from the center. That's not very good because it means that we would have to be in a special region of the universe. But this is because the symmetry we have is spherical. We have spherical symmetry. Right? Now, if we have a more complicated pattern of homogeneity, then that's no longer the case. Then we are not restricted in this way.
This is only true for LTV.
It's true for spherical symmetry. Spherical symmetry is what, now, all these compute people have only worked with spherical symmetry.
Oh.
Now they saw spherical symmetry doesn't work, said rubbish, throw away. Homogeneity, not work, doesn't work. Say, hey, robot, come. But there is a very simple inhomogeneity. That doesn't work. Compute. Talk with walls. They don't care. They don't, because also more general geometries would require a lot of numerical work. But nevertheless, it will happen. It's a future development because it's necessary. Okay. Now we live, as I wrote here, we are at the center of these very large voids, and we consider the radial null geodesics. Now, these are the radial null geodesics. Radial null geodesics, they go along radial rays. These are geodesics that go in the radial direction, but they are null geodesics. And the redshift can be calculated by this formula. This is in general. Now, this would be one geodesic for, let's say, for an FLRW. This is the, see, this is just to show you that in an LTV model, to express a geodesics parameterized by redshift, you have these equations. See, these equations follow from the metric, and they are quite elaborated, but they can, what I want to show you here is how the null geodesics for an LTV geometry are very much more complicated than the null geodesics for a Friedman-Robertson-Walker. For Friedman-Robertson-Walker geometry, essentially the redshift is a very, very simple algebraic relation between the redshift and the scale factor. But with an LTV model, the relationship between the redshift and the scale factor, this is a scale factor also, remember this was, we used to call this H per. No, this was H parallel, right? But then also, it's complicated. The relationship between the scale factors and redshift in FLRW is first, it is not an analytic relation. It's a relation that has to be obtained by solving a differential equation. So finding the null geodesics in LTV geometry is very complicated. Therefore, you can, this is the reason why you can explain observations, because you have more degrees of freedom in the geodesic equation, right? Now, let's see how does it look. This is the Hubble diagram. This is the Hubble diagram. What you see, the dots, this is a relationship between luminosity distance and redshift, okay? Now, this is the data that comes from the brightness from the observations. I see a supernova. I measure the amount of light. I use the fact that this is a standard candle, and I compute the distance. And I plot this distance with a redshift. So this is the data, right? And the blue curve is how can I fit the data with an LTV model. And the red curve is with a lambda CDM model. And we do statistics. Now, if instead of, it is not shown here, but if we would take an FLRW geometry, but with zero cosmological constant, it would be like, it would go like this. Like an FLRW geometry, right? With zero cosmological constant, the curve would be like this. Would completely fail this data, right? Would completely fail this data. But if we have zero cosmological constant and an LTV, we nicely fit this data, right? Because we get a different null geodesic. And so we can easily, like for example, let's take this supernova. This supernova here, redshift 1, and we observe that it has a certain distance. This is expressed in this is some funny astronomers, the modulus and so on. It's distance. It's distance expressed in a very strange form, in a very ad hoc form that the astrophysicists like. But this is distance. This is a measure of distance. Now, we see this supernova is at this distance, right? Okay. Now, or let's take this. This one is a better case. This supernova, it's at 0.5. Redshift is 1/2, and distance is this value, right? Now, I could never get this explained with an FLRW geometry with zero cosmological constant, because the theoretical curve based on the null geodesic would be like this. So it would be very far away, right? So if I'm using an FLRW geometry, I have to put cosmological constant so that the curve can explain this, right? Now, if I change geometry, then I can find a model, an LTV model that will explain that without cosmological constant, because I have a different null geodesic, right? Okay? So the luminosity, the theoretical luminosity distance versus redshift relation is going to be different, right? So I can explain this data. So this is basically that's the trick. That's essentially the trick.
These error bars are 1 sigma error bars.
What? Sorry?
Error bars. These are
Error bars. Yes, these are error bars. You can say that error bars are large because we're dealing with very far objects, and also because supernova type A, I mean, they're not identical clocks. They have differences between them. They're not machines, identical machines. Well, they're machines, but they're huge. These are stars that explode and die. Stars of about, I think, 20 solar masses, very large supergiant stars.
So
Now,
this
yeah.
dashed line is represent the FLRW with lambda CTM, no? With lambda.
Yes, exactly.
And the blue line is
It's an LTV model.
LTV model.
Okay, this quantity here is what the astronomers call the distance modulus. and it is related to the fifth power of the luminosity distance as a function of redshift. But then, because we're talking about small redshifts, normally this distance is expanded as a power in powers of z. Although here for large distances, then this expansion would require many powers. But for small redshifts, this maybe 1 or 2 powers is okay. So normally the parameters are chosen by taking this is observed, and this you obtain theoretically. So you check. This is a theoretical estimation, and these are data, right? But we take this theoretical estimation and expand it in powers, and then we use this expansion to fit the parameters, and we compare coefficients. For example, for an for a lambda CDM, these coefficients can be easily explained by the parameters of the model, which are lambda mater, lambda omega. Right? They can be easily explained. If this is zero, then already at the level of the second expansion, FLRW geometry with lambda equals 0 fails. Already at second expansion. See, that means that already here, see, because the curve for this type of models would be like this, right? So already for very small redshifts, we can say that FLRW models without cosmological constant ruled out, because already at this series expansion at the first coefficient, this is already failed, right? However, LTV models, we can explain coefficients to very high order with the parameters of the model. These are the parameters of the model. So this is essentially what happens. You get these curves, and first you look at how these curves, that you have this theoretical prediction, and you expand this theoretical prediction in series, and you see up to what order of the series the models are still working. And it turns out that LTV models are very robust in this sense. They can explain to very high orders. And of course, there is a lot of statistics involved, because you have a sample of, and you do best fitting and likelihood and so on and so on and so on. But then, anyway, what's important is that you understand why the LTV models can fit observations without cosmological constant. Now, what happens is that, hopefully I have time to present this lecture as well, so I'm going to show for what observations LTV models fail. Supernova, no problem. CMB, provided we are at the center. Then BAO and determination of Hubble constant, tension, but it's possible to explain. But then there comes an effect that is called the kinematic Seldovich-Suniayev effect, and that completely destroys the model. But that's not possible to explain with the models. And then there are other more tests and so on, because it's, again, these are very simple models, so they can explain 1, 2, 3 observations, but there comes a point that they cannot explain observations. It's like making a Porsche or a Jaguar or a very, very sophisticated car with the materials of the motorcycle. You can't, right? So now, okay, so this let's see. It's are we having a tea break? Yeah. Okay. And then the exam, right?
Yeah.
And then afterwards we have more classes.
No, validity function. No?
Validation.
Eh?
Validity function.
Okay, but that's at 3 o'clock, no?
Yeah.
Okay, but there's nothing more. Okay. Well, what follows here it's a review of what we have seen, which will go fast. But then there are other nice theoretical things. But here the point I wanted to convince people is that LTV models are nice because whenever you need inhomogeneity, here, why was inhomogeneity needed? To explain observations, right? Explain observations without assuming dark energy of cosmological constant. This is very interesting because all this fitting of the lambda CDM model. Lambda CDM model is the model that best explains all these observations at large scales. Okay. Now, it's very nice, but then the question arises: what is dark matter? What is dark energy? What the cosmological constant? What is it? So as long as these questions are not answered, then we might be just working with epicycles. We might just remember that Tycho Brahe, and working in his observatory in Denmark, was able to predict every single movement of the planet. He has his theory of epicycles, which was very complicated, but could predict every observation, but it was very complicated. Now Copernicus comes, says, I can also predict the same, but with a very simple theory. So Tycho Brahe, bye-bye. Okay, now, what happens here? We have a theory, the model, the lambda CDM model, predicts everything. So what are the epicycles? In the dark things, right? So inhomogeneity is apparently very complicated, much more complicated than FLRW geometry. But it removes the need for dark energy. No need for dark energy. So the epicycle, which is the dark thing, is gone. It's technically more complicated, but it's conceptually simpler. Now, this is speculation. What I'm saying is speculation because we don't know. But there is a very strong reason to consider inhomogeneity as a way to explain observations. It involves a lot of technical difficulties, but it simplifies matters conceptually. So in a sense, it could be removing epicycles, right? But then people say, no, but you are also putting other epicycles here because, again, you are saying that spherical inhomogeneity is not good. But then you are going to put very special type of inhomogeneity, and that will be another epicycle. But that's wrong, because if I assume inhomogeneity of a certain type, I could explain probably supernovae, CMB, but that assumptions on inhomogeneity has also to be tested with galactic samples. I cannot say that galaxies are put here and here, invent a distribution of galaxies. There is very nice fits observations, but then astronomers are constantly making catalogs of galaxies, right? And then say, yeah, look, but your distribution is not what we observe. Then model is ruled out. So it has to satisfy a lot of constraints. And now, what's the problem? To get all these galaxy catalogs, it's very difficult because what we see from the galaxy is we see a redshift and a position somewhere, right? So it is like what we observe is two-dimensional, right? So how do we get the third dimension? By redshift, right? But the redshift will depend on the model, right? So how we construct a three-dimensional picture of the galaxy distribution, given the fact that all our data is two-dimensional? Difficult problem, not easy. Anyway, the question is that inhomogeneity is very useful, right? It's very useful.
And for star formation and all structure formation, we
No,
need.
no, that's true. That's also true, but this is at local scale. Nobody, not even the most dogmatic astrophysicists, compute, will deny that the universe at local scale is very inhomogeneous. The issue with these dogmatists at this scale is that they say, yes, it's inhomogeneous, but it's Newtonian. So they have one way to get rid of general relativity because of non-perturbative general relativity. Say, yeah, it's true. Of course, structure formation is very inhomogeneous and so on. You are right, but it's Newtonian. So LTV models, GR, all that, wrong. It's all Newtonian, right? That's another issue there. But it's true. No, but in homogeneities, even at large scales, at least, it's important to check it. Like, for example, suppose that LTV models have now been ruled out as models to explain large-scale observations. Large-scale supernova are far away. So large-scale, we're sampling large scales. So LTV models have now been ruled out. They explain supernova, CMB, but there comes a point they fail. Now, was this effort worthwhile? Yes, absolutely yes, because if we had not done that, then we would have been just speculating. We would have been all these people who say, no, but the epicycles and the theories and blah, blah, blah. This speculation is philosophy. The real science is to test the models, right? So the fact that LTV models there was a time like, say, between 2007 and 2012, there may be hundreds of papers that were published on LTV models trying to fit observations. I think like 200 papers at least, or more. It's a lot of effort. It's a lot of effort. Now, the result was negative, but a negative result is good. If I know that this is not true, that is not supported by data, that this theory, this explanation does not explain data, that's a very important finding. If this is not done, then my acceptation or rejection of the theory is philosophy, not science, not hard science, right? So it was a very good thing to do this effort, okay? It was very good. It's very good. It is very good that it was done, even if the result was negative, okay? Now, what remains is to go beyond, to test inhomogeneity beyond spherical symmetry, right? And this is where I'm personally involved, right? Here, this is what I'm trying to do, okay? So, anyway, the rest of the talk will continue tomorrow. It's going to see several theoretical aspects of the models, like treating them as dynamical systems. I'm not going to show you the technical detail, but just the results, so that you see how this is done and what information we get. And then I'm also going to talk about Sekkere's models, which are the inhomogeneous models, because you can say, well, okay, so LTV models are spherically symmetric, so they are limited. So what's beyond them? Sekkere's models. So our models are also analytic, and but they have a lot of very nice properties, and they are far, far more powerful than LTV models. But they are not very well known, and this is another thing I'm personally involved. Okay, so continue tomorrow then. Okay. Okay, so good luck in your test.